Hey Phys C kids, Campbell here. In this video, we're going to talk about air resistance, which is literally a drag. We're going to talk about linear air resistance and a little bit of quadratic, but that's a little more math than you need. But air resistance basically affects the range of objects. Like when we did the rocket lab in AP Physics 1, most of the time your rockets didn't go as far as they should. Well, that's because of air resistance. So let's talk a little bit about air resistance. Air resistance is known by a couple names, but I like to call it drag because it literally is a drag. A lot of times we're going to call it a resistive force in problems. But basically it slows down an object as it passes through a fluid. And a fluid isn't just a liquid, it could also be a gas like air. Drag always acts opposite to the direction of velocity. So it's kind of like friction in that way. But it's also a function of velocity, and this is why we didn't do it in AP Physics 1, because it's a variable force. And so as the speed goes up of an object, velocity goes up, so does the drag force. Drag is also a function of the shape of the object and the density of the object and the fluid it's moving through. So even drag is like different depending upon what object we're talking about. Eventually, drag will impose a terminal velocity because we'll see that as velocity goes up, the drag force goes up until eventually, especially for an object like that's falling through the air, that drag force will be the same as the weight of the object. And so terminal velocity is awesome because it's mathematically easier to deal with. So let's look at the direction of the drag force. As I said, it opposes velocity. So if I take a ball and I throw it up and it comes down, in the beginning, the drag force is actually in the same direction as the force of gravity. But as the object slows down, the drag force gets less because the drag force, we'll see, is proportional to the velocity. Of course, eventually up at the maximum height when I throw a ball straight up, the object stops, so there's no drag force if there's no velocity. But as the ball starts to fall, again, the drag force is the opposite of velocity. So the ball's going down, the drag force is up. And so that means that the drag force is opposing the force of gravity until I get to this situation where the drag force is equal to the force of gravity, and I fall at terminal speed. So which is higher, the magnitude of the acceleration going up or the acceleration going down? Well, if we deal with Newton's second law, right, sum of the forces equal mass times acceleration. And let's call the down the positive acceleration. Then I don't have to worry so much about negatives. In this first scenario of the going up, right, going up, we have that the force of gravity plus the drag force is equal to ma. But on the way down, right, we have the force of gravity minus the drag force is equal to ma. So if you said that the acceleration is higher going up than going down, you are correct. So which takes longer, going up or going down? What? There's no up-down rules anymore? It's not the same? No, right? If I have a higher acceleration going up, right, the rate of change of velocity is higher, which means I'm going to stop faster. Coming down, my rate of change of velocity is going to be less, right, because my acceleration is less. So it means it's going to take longer coming down than it does to go up. So it's going to stop quick, but then take longer to make that same path down. I'm telling you, drag's a drag. This is the only time drag's not a drag, is when we reach terminal speed. Terminal speed is when we get an equal force between the drag force and the weight of the object. And when that happens, right, that's Newton's first law, sum of the forces equals 0. That means we are traveling at, that's supposed to be an O, constant velocity. Constant velocity. So the drag force then is just equal to the weight. So that'll be great because I'll be like, oh, what's the terminal speed? And you'll just say, well, the drag force is equal to the weight. Boop. Done. Or, you know, some fun stuff like that. Let's take a look at a velocity versus time graph for an object that's falling. Remember, when it's falling, the drag force is opposing the force of gravity. If there was no drag force, if we lived in physics fantasy land, right, then we would follow this nice straight line here whose slope would be the acceleration due to gravity. But we don't live in physics fantasy land, and so when an object falls, it has this drag force that's slowing it down. And the faster the object goes, the more the drag force acts. And so we see this exponential decay here where we get to the point where we reach terminal velocity. So terminal velocity is now where it's not that we're not moving, right? It's not that we've stopped. It's that we now have constant velocity. So let's take a look at the equation. So the force of drag, there's two different types. There's a linear type, we call that BV, and then there's the quadratic type, which is CV squared. And B and C depend upon the shape and size of the object, the density of the object, but also on the properties of the fluid and the density of the fluid. Now, B, this linear term, is more important at low velocity, and C is more important at high velocity. But it's usually either the linear or quadratic. It's usually not BV plus CV squared. They're just in the same equation here, just so from a talking point standpoint. But usually you have either BV or you have CV squared. Now, usually most big things, faster things, follow that quadratic term. So things that are moving fast, like a baseball or a car, follow that CV squared. Smaller things like dust particles and maybe coffee filters will follow the linear term. So, however, the quadratic term from a math standpoint is beyond the scope of this class, so we're just going to pretend that everything follows that linear term. So let's take a look at one type of problem. Let's say that the only force acting on this motorcycle rider is the force of drag, and that our equation for that force of drag is negative BV. Negative just means that it's opposing the direction of the motion of the object. So what we're going to do is we're going to write a Newton's second law equation, then we're going to write a differential equation that could be used to solve for the velocity of the object in terms of time. Then we're going to solve the differential equation. Okay, so the first thing we're going to do is always draw a free body diagram. So up here, I'm going to draw the free body diagram of my motorcycler, right? He has a weight, and of course he has the normal force. And then he has this force of drag that is opposing his motion. So obviously the acceleration of this object, if we write a Newton's second law equation, we would say that if it's accelerating in that direction, then the force of drag, the negative force of drag, is equal to ma. And so our force of drag equation is this BV. So don't negative the BV. It's just negative BV is equal to ma. But if I want to write a differential equation, what a differential equation is an equation with the function and its derivative. So the function is v. So how do I do that? Well, we remember that derivative of, or acceleration is the derivative of velocity with respect to time. So when it asks you to write a differential equation for the object's speed as a function of time, what it wants you to do is actually replace the acceleration in Newton's second law with dv over dt. So we're going to rewrite that negative bv is equal to m dv over dt. So to solve our differential equation, what we're going to do is we're going to, what I like to call separate, integrate, integrate. So we're going to first separate our v and t terms. So that means I'm going to put v on this side and I'm going to put all the other crap on the t side. So I'm going to move t over here and v down there, and I'm going to move m over. So when I do that, I get negative bv over m. So I have all my constants on this side with my dt. And on this side, I have dv over v. Now we're going to integrate. Integrate. And our limits are going to be from t equals 0 to t. And my velocity is my initial velocity, which I'm just going to call VO, to the final velocity VF. So we're going to put our little integral signs here from 0 to t, and our integral signs here from VO to V final. Now, the integral of a constant, right, is like, so that would be like that was t to the 0 power, right? So we add 1, we divide by 1, and so we would have negative v over m t. And it's from 0 to t, right? So 0 would just be 0, and so with the t, it's just that. On the other side, if I take the integral of dv over v, that's the natural log of v. So that's an integral of dx over x is the natural log of x. So dv over v would be the natural log of v from VO to V final. All right, so now I gotta do the limits. So that's negative bt over m is equal to the natural log of V final minus the natural log of V initial. And by natural log properties, right, when you subtract natural log, it's like dividing them. So bt over m is equal to the natural log of v final over v initial. Boom, natural log property. Okay, we're not done because we're gonna get rid of that natural log by eing it. So we're gonna put a little e under both sides here. All right, and when we do that, on this side we get that exponential function of bt over m, and that's equal to v final over v initial. And now we just got to solve for v initial by moving over the VO, and we get that v final is equal to VO times e raised to the power of negative bt over m. So it shows that the velocity is an exponential function. Woo! Wasn't that fun? So now that we have our velocity equation, if we wanted position, right, we'd just take an integral of that velocity function. Don't worry, I'm not going to ask you to do that. But let's just take a look at graphically what that would mean. All right, for our velocity equation we just derived, right, we saw that it was an exponential decrease. So as the velocity increases, the drag force increases, which then slows down the velocity of the object until we reach our terminal speed. But from a position standpoint, right, we're still gaining position. It's just that we're gaining position at a slower rate. So this would be what our velocity and position graphs might look like. Now, what about a ball falling through a medium? Now our force of gravity equation is going to be different. So let's take a look at this one. This one's a little more complicated. So we're going to write a differential equation for the instantaneous speed of the ball as a function of time. Now, if you're not in calculus right now or have ever done an integral like this, a u substitution, we're going to have some fun now. So the first thing we're going to do is we're going to write our Newton's second law equation. Right? Here's our free body diagram. The object is accelerating down, and we're going to say that that's the positive direction because it makes life easier. So we have the force of gravity in the positive direction minus the drag force, which is BV. Again, don't double negative that in the equation. And then that's mass times acceleration. But we want to write our differential equation. So that means we're going to go mg minus bv is equal to m dv over dt. All right, we're going to separate, and then we're going to integrate. All right, so that means we're going to move all the constants over with the t, and we're going to move the things with velocity over onto the other side. So what that means is over on this side, we have 1 over m dt is equal to dv over mg minus bv. Whoa. And we're going to take an integral from 0 to t. And this says it starts at rest, which means that its initial velocity is 0. So that means we're going to go from 0 to some velocity v. All right, well, this side's easy, right? That's just t over m, right? The integral of dt is just t. And so we have our m, and it started at 0, so that's cool. But what do we do about this side? I mean, we've got this mg over bv. What? Well, there's a couple different ways, but I'm going to show you u substitution. So in a u substitution, what we say is that we're going to say u is equal to mg minus bv. And so on this side, that I'm going to make this dv over u. Okay, well, yeah, great. There's no v in there now. How do I do that? It's not like use v. Well, I'm going to go back over here, and I'm going to take a derivative of u as with respect to, oops, I almost put a t, v. So du dv. So if I take the derivative of this with respect to v, right, this is a constant, so that would just be 0. This, right, when we take a derivative, right, we subtract 1 and we multiply by the power, so that would just be negative b. So that means that du over dv is just equal to negative b. And so what I want to do is I want to get rid of this dv, so I have this in with regard to u. So I'm going to solve this for dv, so I can substitute it in here. So that means that dv is equal to, I just bring that down and bring that up, right, that's du minus b. Okay, so I'm going to take this and plug it in here. Okay, so we're going to have t over m is equal to the integral from 0 to v. Instead of dv, we're going to put du over u, and this I'm just going to put times 1 over negative b. So let's do this though, because that looks kind of funky. Since this is just a constant, right, we could just pull it out, which means we can just pull it out and then just move it over here, right? Because that would, like, we could say that would be 1 over negative b, integral of 0v, du over u. So let's just take that and move it to the other side. So all of the constants are over on the other side. So that would be negative bt over m is equal to the integral of 0 to v of du over u. Oh, well, we just did that, right? The integral of du over u we just did. That's just the natural log of u. So we have negative bt over m is equal to the natural log of u from 0 to v. Well, what do we do now? Well, get rid of the u, right? We said u is mg minus bv. So we're just going to plug that in for u. So we get negative bt over m is equal to the natural log of our mg minus bv from 0 to v. And so when we distribute our little limits there, right, that would be the natural log for v, right, that's still mg minus bv. And then subtract from that the natural log. If this is 0, right, that term goes away, and then that's just mg. Now, property of logs, right, when we subtract logs, that's like dividing. So we get negative bt over m is equal to the natural log of mg over bv divided by mg. Coolio. Well, now we're going to do the whole e-it. All right, we're going to put an e on both sides, and that gets rid of the natural log. And so now we have e to the negative bt over m is equal to, so that just goes away, mg minus bv over mg. All right, now we want to solve for v, so that means we got to do some rearranging, and I'm kind of running out of space, so let's just move over here. All right, we're going to move the mg to the other side, so we have mg e to the power of bt over m is equal to mg minus bv. We want to solve for v, so first let's multiply all the stuff by a negative. So we'll get a negative, and a positive. And so then we're going to move this over, and so we'd have mg, so we're going to add mg to both sides, mg minus mg e to the power of negative bt over m is equal to bv. And we can factor out the mg, we can move the b over, divide both sides by b, and we get mg over b, 1 minus e raised to the power of bt over m is equal to b. Wasn't that fun and exciting? All about the u substitution. Will you have to do one of these? Absolutely. So you may need to watch this video a couple times if you are new to the whole calculus thing. So, wasn't that fun? Let's do some of these in class.